Good morning, everybody. My name is Bruce Lieberthal, and I am the Chief Innovation Officer at Henry Schein. Really thrilled to be with you all. We have an exciting day for you planned, and we'll begin with three speakers that I'm going to introduce to you. Just a couple of things before we start. Each session will be about 25 minutes, and we'll leave 5 minutes at the end during that 25 minutes for Q&A. And I just want to mention one thing that should you have questions, please post them in the Q&A box to your right, and we'll pick them up during the presentation and ask them on your behalf. Our first speaker is Dr. Jinfang Wang. He comes to us from Yokohama City University, where he is professor and dean of the School of Data Science. Dr. Wang was appointed Dean of Data Science and Chairperson of Division of Data Science, Graduate School of Data Science at Yokohama City University in Japan in April 2020. Before joining Yokohama City University, he was Professor, Department of Mathematics, Chiba University in Japan, teaching and doing research in statistics. His talk today is titled A Convolutional LSTM Model for Predicting the SARS-CoV-2 Positives in Japan. Dr. Wang?
Thank you very much. Thank you very much for the nice introduction. My name is Jinfang Wang from Yokohama City University in Japan. We will be at midnight, 2 hours later. This is a joint work with one of my graduate students. I'm going to talk about not the details, but the general idea of how can we do something to predict the COVID-19 positives, not in Japan, but in Tokyo. Our model involves convolutional recurrent neural network called LSTM, the long short-term memory neural network. We will use the data from the metropolitan Tokyo government from 2020 from the February of last year to the end to August of 2020 this year. This is the cumulative positive numbers of infected people of Tokyo. We will show you how we may look at the data from different disciplines, and then I would focus on the neural network approach. First, I would like to talk about how traditional statisticians look at this kind of data, and then I will talk about the current research, the hot topic on dynamic compartment models, which are defined by ordinary differential equations. And these models are limited due to the unrealistic mathematical assumptions. And then I will talk about how we may use convolutional recurrent neural networks to predict the number of infectious people. And we will not focus on the technical details, but just give you a rough idea how we may do data science from different viewpoints. I will focus on part 3. Traditional statisticians look at the time series models from various viewpoints. One of the popular model is called the autoregression integrated moving average model, which is a combination which is represented by equation 3, which is can be decomposed by two parts, the equation 1 and equation 2. This it can be applied to stationary time series. After taking one order difference of the infections data I just showed you a few seconds ago, we can look that which much more, but it's not stationary, but much more stationary than the original time series by checking the autocorrelation function and the partial autocorrelation function at the bottom. We can roughly get an idea about the two numbers, P and Q of equation 1 and 2. Then we can do prediction using equation 3. This is a prediction using 1 year data about the next month. You can see we have a large confidence band, which is not good for this kind of time series. I just show you how statisticians may look at this kind of data. It does not work very well. The current research on prediction of the infection numbers focus on the dynamic compartment models, which is not very realistic, but very very simple to understand. Ignoring the births at the top, we divide closed population into 3 compartments called suspected, infectious, and the recovered. We ignore the births, and the errors describes the flow of the dynamics between the people, among the people in the 3 compartments. These numbers depend on time t, and the compartment models describe the dynamics by the ordinary differential equations governed by from equation 4 to equation 6. The Greek letters describes the characteristics of the disease. We will not go into detail about how we can understand each parameter. This is called SIR model, SIR, which depend on T, but we omitted the dependence on T for easy readability. For 7 days prediction, for 1 week, you see the blue prediction. The blue lines represent the prediction of the real red numbers. It does a good job for 1 week prediction, but we will see later it's not good for a long-term prediction. It's unrealistic, just as I emphasized previously. There are 2 fundamental problems involved about the SIR models. Assumption 1, that the infectious individuals are independently and randomly mixed with all other individuals, which is an unrealistic assumption. And assumption 2, the infectious process is irreversible. We cannot go from the bottom. Once a person recovered, cannot get infected again, which is unrealistic for COVID-19. This is a long-term 9 months prediction based on the same SIR model. You can see which is quite different from the realistic observations. There are many other research on refining the simple SIR model. For example, the SUER model is a typical example proposed in the literature, which introduce more compartments. You see the we introduced a new exposed compartment and additional unreported recovered. Even so, the dynamics are very simple. For those who understand the differential equations, you see this is a very simple differential equation, a system of differential equations which are very unrealistic. So to do a little bit more beyond the dynamic models, which are unrealistic, we just try to use spatial temporal information to do a better prediction. That's our motivation for this research. We use the covariates, which consist of the confirmed cases, the recovered, and the populations, the detailed population of each word of Tokyo, and the restaurant information, etc. Our target is to predict the 7 days moving average daily new positives. We do a moving average because we have daily effects, serious daily effects for the medical checkup here in Japan. We use the populations. For example, you see the strong correlation between the number of infection and the population number at each word of Tokyo. We have 23 words in Tokyo. It's almost lines on a straight line. This is a map of Tokyo, which is divided into 23 words. I ignore the neighboring cities, and we have the daily observations of new positives for each of the 23 words. To do a convolutional neural network prediction, we put these numbers into a heat map for at each day for each time point, and also we stack the covariates along the z direction to get a three-dimensional tensor in order for a neural network to learn. I will not go to detail to try to describe the neural network, the general idea about the neural network, because it's so popular, and I think which are learned in most classes. And anyway, a neural network model mathematically is a repeated composition of functions of form of equation 14. You repeat it many times to get a deeper and a deeper network. 14 says if x is activated by the function sigma, which usually denotes a sigmoid function, but not necessarily, which is a function of the affine transformation of x. The W is a weight matrix, and the B is a vector of bias we wish to learn. We minimize usually the squared loss of equation 17 for the continuous case to learn those parameters. This is a detailed description of the convolutional long short-term model. It's a nuisance to describe to try to explain each symbol and what is going on, but I just show you a simple example of the essence of the long short-term model. It consists of three important gates called forget gate, import gate, and output gate. Forget gate, for instance, for natural language processing, For example, if you are trying to understand the following sentences, Japan is a small country. US, on the other hand, is a huge country. After meeting the full period, we are talking no longer about Japan, but about US. Thus, to release the memory, we wish to forget about Japan. That's the functionality of forget gate, which is described by equation 19. On the other hand, the import gate is to remember, to remember useful information. For example, Japan is an island country. Some Japanese eat ramen as well in sushi bars. The information for the model to remember or to keep for the second sentence is not ramen, it's a sushi bar, because it's related to the first sentence, the words of island. That's the smart part of the import gate, which is described by equation 18. The output gate, for instance, if we are trying to process the sentence like Japan is an island country, that naturally explains most eat raw fish. We try to fill out the word after most, that we expect our model to output Japanese. This is the output, is what output gate try to do. And we do the time series prediction using the three-dimensional tensor based on these covariates. This is the proposal of our model to try to predict the infections numbers of people in Tokyo. These are well-known convolution operations which appear at these equations. And diagram describing what the convolutional recurrent neural network do. These are the main results of our application of the recurrent neural network model for the Arakawa word. We see the prediction after the red line. The yellow line is a prediction of the blue observation. We see the last prediction is strongly affected by the previous one, so it doesn't. It's a problem for our future research. We do these prediction for each word, and we add them together to get the total prediction for the metropolitan Tokyo area. To compare our model with, for example, the popular dynamic model, SUEIR model proposed recently for the root mean squared error and the mean average error. Our model does seem to work for the data we tried in our experiments. We do not claim our model will work for each case, but we expect that our model will be can be applied to a wide range of problems involving spatial temporal information. We just tried to apply it to the prediction of infections numbers, but we are interested in other problems as well. This is the final remark. I have just mentioned today. I will not go to the technical details of each of the methods I mentioned. I just would like to mention that there are two cultures in data science. One is statistics. The other is represented by machine learning. Today I talked about machine learning, but statistics statistic methods are more understandable if you wish to put your analysis into business. You are responsible for explaining why your model does the job or do not do the job. So we are interested in something which is between the statistics and the machine learning, but we have a long way to go. The one possible solution is a physics-guided machine learning. The physics part, in the physics part, we respect the physical laws. For example, the laws governing the infectious disease, and we can put those parts into mathematical formulas. And while we respect the data as well to do prediction using deep learning is only one of the possible approach. We may do we may use other approaches for prediction. This is a long-term research. Anyway, my students actually their backgrounds divided into statistics and machine learning. I myself is not a specialist in machine learning. I'm from the statistic background, and I appreciate the precision output by the machine learning algorithms, but the problem is that we cannot explain why they do it good or bad. I think I'm about the time. Thank you very much for your listening.
Wow, that was great, Dr. Wang. Thank you so much for all that great information. I had a question that came to me while I was listening to you. You know, we hear two terms in machine learning used very often these days. One is LSTM, which you just spoke to us about. The other is CNN. Briefly, because we don't have a lot of time, what are the differences between them? Why is one better than the other for certain purposes?
You are asking why machine learning algorithms are usually do a better job than statistical methods?
No, sorry. I was asking why LSTM, what's the difference between LSTM and CNN?
That's actually a combination of CNN and LSTM. We have a time series model, so we use the LSTM, and we try to put the infectious number of infectious people in Tokyo into by projecting the one-dimensional data into a two-dimensional map to do a CNN as well. So that's a combination of the two different types of neural network models. We try to use the advantage of putting it into a two-dimensional map is to use the correlation structure, which can be captured by CNN.
Terrific. Thank you so much. I think that's about all the time we have. So I wanted to thank you for a really engaging discussion. And I know it's very late where you are. So we really appreciate you providing your time and expertise to us. Our next speaker.
Thank you very much.
Thanks again, Dr. Wang. Our next speaker will be my colleague at Henry Schein, Dan Holewienko, and he'll be joined by Emmanuel Ekbo and Akil Iluri. Dan at Henry Schein is the Executive Director of Big Data and Business Intelligence. His talk will be titled, "The Key to Creating Value in Healthcare with Machine Learning and AI." Just briefly, Dan is over a 20-year experienced technology executive in healthcare, financial services, media, education, and retail. He started his career in software development and later focused on overall technology strategy, transformation, and management in mid to large size regional and global organizations. So I'm thrilled to be able to introduce my colleague at Henry Schein, Dan, and his two colleagues, Emmanuel and Akil. Dan?
Thank you, Bruce. And then thank you, team at CEWIT. Hopefully you guys can hear me and see the presentation. Everything looks good. So as Bruce said, I'm Dan Holewienko, Executive Director for Big Data and Business Intelligence at Henry Schein. I'm going to be talking about a slight change in the title, Bruce, the key elements of success in ML in healthcare. And my two colleagues are from Author Solutions, Emmanuel Egbo and Akil Aluri. Later in the discussion, I'm going to hand off to them to have them show the success through a project that they ran, and which is going to contain the key elements that we're going to discuss today. So healthcare, ML in healthcare is rooted. It's growing fast. It's about a 50% compound annual growth rate right now in terms of capitalization in the marketplace and spend. And it's mostly driven by the fact that big data has really taken off, and the demand for faster services, higher accuracy in healthcare, less friction in healthcare services, and reduced costs has really made ML attractive for the use within healthcare. This is kind of just another way of looking at the year-on-year growth. But the interesting piece here is to note that the spend seems to be evenly distributed between software, hardware, and services in ML. Value proposition in healthcare of using ML is really distributed among 5 or 6 different areas. The number one reason, or the number one impact areas today for ML use has been in drug discovery and research. Second being medical imaging and diag. Third being virtual assistant, and then followed by therapy planning and clinical workflow, all making great impact in providing more faster service and more frictionless service to customers. Here's some examples, and I just randomly picked some. This is an arbitrary list, but just so you could see some of the the dynamics that ML's having in healthcare. But Mayo Clinic having a 72% reduction in detection in critical diseases. Hopkins trying to increase the admittance rate. It's got a 60% improvement in admittance rate and a 21% improvement in frictionless discharge. Beth Israel, same thing with early detection, being 90% improvement in accuracy and 95% improvement. And the list goes on. It's not meant to be an exhaustive list. It's meant to just highlight that ML is established in healthcare and it is making a difference. The challenge is that many healthcare organizations are not well equipped to take on ML, and so those have been successful at getting a competitive advantage, and those which are not adopted a program or a strategy for ML or seem to have a competitive disadvantage. And so what we are faced with is ML is driving new services and improved services faster and more accurate diagnostics and outcomes and cost savings, and that's a fact. However, there are numerous obstacles. Traditional technology departments today are not really wired for data science. They're not wired for ML and AI. And Harvard Business Review polled a fair number of organizations and came up with these were the top 6 reasons or obstacles why ML is not it's hard to take root in healthcare. And you can look at this on your. I'm not going to read it, but it is significant, and it really revolves around the complexities. ML to be successful is really a science. It's a science of data. It's a science of model and statistics. I think our prior speaker kind of emphasized that. And without having those rigors, innately built into your DNA, it's pretty hard for you to be successful. I mean, here's just an example of the the type of activities that are necessary for just pure data prep to get into ML. And this mystifies traditional data or technology departments. And then we get right into the talent, right? This is like a normal life cycle for machine learning. And the machine learning dev cycle is not trivial. It's not as intuitive, and traditional departments will struggle to find and attract talent and retain them in the ML area, and they may not even be able to afford them, being that it's such a competitive space at the moment. Now, the low-code or pre-built model arena has really upped the game in trying to make it more simple. It tries to automate, it tries to give you options and models, but it's not a silver bullet. And I like it into putting a hammer in your hand doesn't make you a carpenter. And likewise, putting tools like these low-code pre-built models in the hands of traditional technologists doesn't make them a data scientist. And so we're faced with a dilemma. Gartner predicts, or really asserts, that 85% of ML projects are failing, and by 2022, or actually next year, they're assuming that the trend will remain the same. And so, how could all of this success be talked about, and yet the success of the failure rate be at 85%? And that's what I want to kind of get into is that there are certain ingredients that I wanted to summarize that really pin a more likely success, a more likely outcome of success with ML. And I just want to kind of enumerate these and then hand off to my partners to talk about a use case which has kind of adopted these 8 things. So the first one is admit that you need help. Admit that you should be picking a domain ML partner. You're coming at it, maybe your first rodeo, your second rodeo, whatever it is. Pick an ML expert, pick somebody that's got healthcare domain expertise, and maybe even an SME that's in your particular problem that you're trying to use ML for. Don't do it yourself. It's a real mistake, and you might think it's cool to do. Yeah, it's cool to do, but it's not so cool to fail. So you might want to get help. Simply start simple and gain success, and then build on it. That's a model that probably applies to a lot of things in life, but in ML, it's critical. Start simple and succeed simply. Adequately define the problem and the target KPIs. I think I can't stress this enough. People start, going right into ML when they don't clearly understand the problem and the nature of the data for the problem, and they don't understand what is the measurement for success. And so this becomes a huge pothole in the road to success. And I would highly pay attention to this one. The next one is kind of goes hand in hand with the partner. They should be bringing scientific methods and processes. Again, not that traditional technologists don't have processes and methods, but this is really science, and it's highly scientific, and there is certain methods by which you got to treat science data, and you got to keep variables separate and isolation, and it's if you don't have these processes down, you're doomed. This next one is probably one of the top reasons for failure, is where people enter ML without adequate data and adequate samples of data across the spectrum of use cases, and inadequate data is probably one of the top 3 reasons for failure. So not having enough data or not having all your data represented across your scenarios is probably is doomsday for you in ML. But leveraging the pre-built models and pre-trained models is just a way to get there fast. No need to start from ground zero. But I think, again, just having a hammer and swinging it, in an untrained hand, it could lead to disaster just as much. So again, having that partner who's experienced to leverage pre-built, pre-trained is a combination of experience with speed. Scout and test and pick the right models. I think when we talk about the use case today, you're going to see that in their use case, they tried several different models before they settled on one. because they were getting varying results. And I think you need to understand that it's not perfect. The first model you pick may not be the model you wind up with. And testing, retesting, switching, comparing is really a very common thing and an expected thing in machine learning if you do it right. And this last one, keep retraining. It's not one and done. Don't get too comfortable with what worked today as your ML. You've got to keep retesting your data and reassuming, did your outliers get handled properly? Did you retune the model to handle the outlier cases properly? So it's not a one and done. This last one is not really part of the 8, but it's just an edict you should consider, and that is know when to walk away. Not every problem is an ideal ML problem. And just because you've invested time, energy, and money, you may need to close up shop and say it's not ML. So what I'd like to do now is explore a successful use case in ML. I'm going to introduce my my 2 colleagues, Emmanuel Egbo and Akil Aluri. They're from Arthur Solutions, who focuses on big data, data science, and analytics, as well as ML and AI solution implementations. They're going to walk through a successful use case in healthcare using ML that employs these 8 ingredients. Emmanuel, off to you.
Thank you, Dan. And once again, really happy to be here. Can you hear me okay? Okay. So the healthcare space has been experiencing big data long before big data became mainstream. And however, what machine learning and artificial intelligence affords us today is the unique ability to predict future outcomes using historical patterns. And this use case features an urgent care provider, and I'll give a quick background on the problem statement. So as you know, urgent care clinics are organized differently from the traditional primary care clinic. One of such distinction is urgent care don't have the luxury of scheduling in patient appointments in advance to know and control the volume of daily visits they get at every given time. And this poses a number of problems. One of such notable problems is increased wait time that this client reported during the discovery phase for this project. Also, resource costs, impact on their profitability, quality of care, and patient satisfactions were some of the major pain points the client reported. And the client was basically seeking exploring ML solution to this problem, and I'll run you through the project implementation. Then next slide. So going into this project, the client had several expectations in terms of outcome. One top of the list is to find ways to better allocate their resources. By that, I mean, helping clinics to staff appropriately was one of such expectation, and also improving the overall patient experience, starting from little to no wait time to see a provider, and also ensuring that their resources are distributed across clinics and they have the right amount of resource at every given time. Also to develop an AI based analytics culture within the organization to improve operational efficiencies. Next slide, Dan. So for this implementation, we had employed the 4D machine learning lifecycle approach. And this approach features at very high level 4 main stages. The data discovery, and just to note that ML projects overall, from our experience and from others' experience as well, tend to be very data management intensive. So the discovery phase featured data ingestion, integrating data from disparate sources, could be EHR, appointments, scheduling system, different sources, and also cleansing and transforming that data, preparing it for your ML or AI model, as the case may be. The design phase featured prototyping, coming up with the technical and business requirement, as my colleague Akil will discuss in detail in the following slides, and also the development phase. In addition to what Dan already showed us, testing, retesting is important, and the last phase to operationalize the model when you have a fitting model to your use case or problem. Finally, some backstory to this project is this client operated 109 clinics, and just to build on what Dan already said, making sure you have adequate data is very critical. It's a critical success factor from our experience implementing this project. So we found out in the last minute that the client had recently acquired a smaller urgent care practice with over 34 clinics that didn't have enough data to be onboarded into the ML solution. And at that point, we made a decision to segment the clinics into different groups, and we categorized those with at least 2 years of historic data that would fit the model into the matured clinics group, and the other clinics were left out of the model and onboarded subsequently as they became matured, and by that having enough data to produce the right results in the model. And Akil would provide more details on the model evaluation process, some of the data preparation steps we took for this implementation. Akil?
Yes. Hi, everyone. I'm so happy to be here. So let's look into the steps which we go through. So we have 3 main steps in any machine learning development phase of a model. So we have data preparation, we have data cleansing, and we have the tool stacks which we'll be using there. So when it comes to the data preparation, why this data preparation step is really important is because not all the data which is readily available can be used and can be consumed by any machine learning model. We need to do certain kinds of transformations. We need to make sure we create a separate data model for our AI or maybe an ML project, whichever we name it. And it would be easy for us to manage and optimize with respect to our use case. So when it comes to data cleansing, again, we would be having a lot of missing values. We would be having, we might be observing that the data is not standard between each and every variable. So again, there we need to standardize all the data elements based upon the use case, and we need to even do a couple of missing value imputations again, and then make sure it aligns with our business use case. And here, when we were developing this use case, we have used Pyramid Analytics as a BI platform, and we also have used Azure Data Science, which is called ML Azure Studio, which is there on the cloud. Next slide, please. So this question always arises. So why do we need ML and AI when we already have a traditional methods? So the main difference between AI, ML, and the traditional methods is, so traditional methods usually they come up with a rule based. They are exactly the rule based. They are designed with certain number of rules, and they're gonna end up with a defined population. So they're not gonna predict the future, or they're not gonna tell you what's gonna happen next. It just tells you based upon the rules. Okay, this is what the population lands on. But the main use of ML and AI is it lets you know the future. It will give you the foundation for predictive and prescriptive analytics, and it will also let you know what's going to happen next. Like what you can predict what's going to happen in future. That's the main advantage of ML and AI. And now in a lot of use cases, that's being taken over by a lot of traditional methods. Next slide, please. Okay, in our use case, we had 3 line of businesses in the urgent care. So when we were developing our time series analysis models on each and every line of business, we have landed at a place where we took each and every line of business as a separate individual entity. And if you look at the graphs here on the left hand side, it was for every day visit for a line of business for one clinic, and the same follows for another line of business for the second clinic, and the third visualization at the bottom, it is for the another line of business for client W. So it is like we have 3 line of businesses within our healthcare system, and then this is how their data looks for over a period of time. Next slide, please. Yes, so we saw the distribution there. We saw how the distribution looks for each and every line of business. And as Dan was mentioning, trying many multiple machine learning models is really, really important, because not each and every model is being, or it's suitable for a particular use cases. For here, what we have done, we have explored ARIMA model on our use case, and we have also looked into Holewienko method. But when we compared the evaluation metrics for both of these models, the evaluation metrics was not so compromising, or not so prominent when it was ARIMA model and it was Holewienko model. But we have deployed a model called Profit model. We have developed. So this is a model which is being developed by Facebook, and it is already a pre-trained model. So it's in a state where you just take the model, give all the details which you have in your use case, and then it predicts, it gives you the predictions depending upon the data whichever you given. So it's already a predefined model, and it's been a stable model, and this was giving more prominent results when we compared with ARIMA and Holewienko method. And as Emmanuel was mentioning, this healthcare system has evolved, has overtaken a few amount of urgent care clinics at the last minute. So we have divided the entire predictions into two kinds. One, the clinic P with greater than 1 year, and clinic P, the other clinic which is less than 1 year. And you can see the distributions how it looks. And next slide, please. And over to you, Emmanuel. Thank you.
Thanks, Akhil. So just a quick summary. I'll make it fast because of time. It's always important to understand what goes into these projects as input in terms of resources. And on the screen, you see the composition of the project team. We had data scientists, ETL developers, a DBA, and also a business analyst, a healthcare SME, very critical to provide specifics of the use case, and a project manager. So the first 3 resources are on the technical side, and the later 3 are on the business side. We have a framework for ensuring success with the ML projects to implement at ATA. One, in addition to what Dan already told us, making sure you have the right skill set in your project team, and also identifying and taking advantage of accelerators. That could be for ML solutions. Cloud is typically the first go-to for many reasons in terms of scalability, reusability of some components, and infrastructure as a service could be an advantage as well. And very important, making sure you have the right partner that have understanding of your problem and have shared vision and can have the capacity to deliver. In terms of resource, this project took about under 200K, a span of 3 months, and we evaluated different models to come up with the right fit for the problem, and it's also data intensive. I'll skip the next slide and go to the results for the sake of time. Dan? Yeah. So summary of the outcome of the project, our client reported over 85% improvement in resource allocation across clinics, especially when you're an urgent care service provider with over 100 clinics. This is a huge result in terms of resource management and profitability. So there's also 50% improvement in staffing, which was one of the core issues that prompted this project in the first place. Clients saw some increase in patient satisfaction survey, about 25%. And lastly, the client was able to decrease the wait time of patient experience before seeing a provider by 75%. And with that, I'll turn it back to Dan to give us some closing statement.
Right. Thank you, Emmanuel. So just to ML has prevalence and growing within the in the healthcare space. It does offer a competitive advantage, and laggards will be disadvantaged due to competitive pressure. Projects have significant obstacles and complexities, and so and the failure rate is high. So our assertion is really there are 8 ingredients to success. Pick a partner, stay simple, adequately define the problem, keep your KPIs for the success in sight, employ scientific methods and processes. You have to have enough data for all your scenarios. Leverage pre-built and low code. Picking the right model and keep iterating, I think, are the key elements to where we've seen success. And just knowing when to walk away, knowing when to pack it in. So, with that, we're going to entertain any questions. I know we're out of time, but I just wanted to kind of wrap it up there for you, Bruce.
Thanks, Dan and Emmanuel and Akil. Really great presentation. I wish we had more time for questions. There are actually some questions in the Q&A section, so maybe you guys can take a look at that and provide some answers back. Actually, one of those questions is from a former Henry Schein member, Nat Monroe. Anyway, we need to move on to the next presentation, the last in my group. And presenting to you now will be Lu Su from Purdue University, where Lu is an associate professor. Lu will talk about towards fine-grained wireless human perception, a little bit about Lu, an associate professor in the School of Electrical and Computer Engineering at Purdue University. His research interests are in the general areas of Internet of Things and cyber physical systems, with a current focus on wireless, mobile, and crowd sensing systems. He received his PhD in computer science and an MS in statistics, both from the University of Illinois at Urbana-Champaign in 2013 and 2012, respectively. Lu?
Okay, can you hear me?
We can hear you fine.
Oh, sorry, wait a second. Okay, so let me share my screen. Okay, thanks for the introduction. Good morning, everyone. It's my great pleasure to have this opportunity to share with you my recent work towards fine-grained wireless human perception. Today, we are living in an interconnected world. Through ubiquitous sensing, computing, and communicating devices, everything in the world is now linked to each other, forming an Internet of Things. In IoT systems, all kinds of the devices including not only the smartphone, laptop, but also appliances and even the vehicle, are interconnected through mainly wireless links. In such wireless networks, traditionally, the wireless signals are used as a communication media to transmit data. For example, as you can see in this room, there is a Wi-Fi access point, which is transmitting wireless signals. The wireless signals can reach every corner of this room. And there are multiple devices, such as the smartphone, laptop, and even a smart TV and a smart printer, who can receive the Wi-Fi signals. However, imagine that if a person present in this room, the movement of the human body may change the transmission pattern of the wireless signals. So the wireless signals may carry some information that can characterize the human activities. So based on this idea, our goal is to take advantage of the pervasive wireless signals to sense human activities. Let's take a closer look into this scenario. We know that wireless signals, when being transmitted, will go to all directions in the space. So it may hit the human body in the room and reflected by the human body. And the human body, when conducting different activities, will change the transmission pattern of wireless signals in different ways. So we can train a machine learning model on the received signals to recognize human activities. However, there is a major challenge to achieve this goal. That is, the transmission of the wireless signals may be also affected by the objects in the ambient environment, such as the bed, chair, and other furniture. So the signals arrive at the receiver may contain substantial environment and subject-specific information. As a result, the activity recognition model that is learned on one particular human subject in one particular environment cannot be directly applied to recognize the activity of another human subject in another environment. To address this challenge, we propose EI, an environment and subject-independent activity recognition model. So our model can make use of both labeled and unlabeled data. It can remove the environment and subject-specific information in activity data and extract the common features that are shared by different subject and environment. And we can use the extracted common features to recognize unlabeled activities. Here, I'd like to give you an overview of our system. We first collect data from different human subjects in different environments. Then we normalize, transform, and segment the collect data and feed the processed data to our proposed deep learning model. Even can output the activity labels. This is the architecture of our proposed EI model. It contains three major components: the feature extractor, activity recognizer, and the domain discriminator. First, the feature extractor is used to extract the low-dimensional representation from input data. And based on the features, we can train the activity recognizer on both labeled and unlabeled data. For labeled data, we can directly maximize their label classification accuracy, actually the training accuracy. For unlabeled data, because we don't have their labels, so we try to maximize the confidence of prediction on unlabeled data in order to drive the classifier's boundary away from the unlabeled data. The third component is the domain discriminator. Here, the domain is defined as the pair of room and subject. The goal of the domain discriminator is to identify from which room and on which human subject the data is collected. Recall that our goal is to remove the domain-specific information from the data. And this can be achieved by negating the loss of the domain discriminator. So during the training process, the feature extractor will be trying to cheat the domain discriminator and at the same time boost the activity recognizer. Once the domain discriminator is fully cheated, that means when it has no idea in which room and on which human subject the data is collected, that means the features output by the feature extractor will contain no domain-specific information. We evaluate our proposed domain adaptation framework on 4 different wireless sensing testbeds, including Wi-Fi, ultrasound, 60 GHz millimeter wave, and visible light. In our experiment, we designed 6 different human activities and employ 12 human subjects. The activities are conducted in 6 different rooms in 2 different buildings. And we labeled data from only a subset of the domains. And there is no common room in both labeled and unlabeled domains. This figure shows the experimental setting for the Wi-Fi signals in one of the rooms. As you can see, the transmitter is a Wi-Fi access point, and the receivers, a couple of antennas connected to the Intel wireless link 5300 network interface card. And we extract the channel state information from the Wi-Fi data. In our experiment, we include 3 baselines. The first one is the random forest, widely used traditional classifier. The other 2 are state-of-the-art domain adaptation frameworks. This figure shows the activity classification accuracy of all the approaches. And as you can see, so the performance of all the approaches improve when the number of labeled domains increase. And our proposed EI framework achieved the best performance because it can utilize unlabeled information more effectively. And in addition to the Wi-Fi testbed, we also evaluate our proposed data adaptation framework on 3 other wireless sensing testbeds, including the ultrasound, millimeter wave, and the visible light. Similar result can be observed, and due to time limitation, so I will skip the details. Okay, I have demonstrated that the wireless signals can be used to recognize human activities, which in fact is to classify the detected activity to a predefined. So this is a classification problem. And actually, when I'm trying hard to improve the classification accuracy, one question comes to me. Can we do anything better than just classifying the activities? Can we, for example, image the human body like the X-ray eye of Superman, who can even see through the wall? Let's first take a look at this video of my recent work, Y-Pose, the first 3D human pose construction framework using commercial Wi-Fi devices. Wait a second.
Three, two, one, go!
Okay. So as you can see in the video, our proposed white pose framework can reconstruct the human skeleton, even if the human subject is completely occluded. So next, I'd like to give you an overview of our white pose framework. We first collect the CSI data from distributed Wi-Fi antennas. And in addition to that, we also use Wi-Con system. Which can generate high precision 3D human skeletons. And we can use the 3D skeleton generated by the Wi-Con system as the ground truth to train our deep learning model. After model is trained, it can be used to construct the 3D skeleton from the CSI data. To generate a 3D human skeleton, an intuitive solution is to directly and independently estimate the position of each joint. However, 2D low spatial resolution and error-prone nature of the various signals cannot be accurate. As a result, it may not be able to keep the relationship among the joints and result in unrealistic skeletons like this. To address this problem, we have some insights. First, the human skeleton can be represented as a tree. Second, in 3D space, the human segments can be as the rigid bodies with fixed legs. So to infer the position of each joint, we only need to estimate the rotation of this joint with respect of its associated body segment. For example, given the initial position of the shoulder, elbow, and the wrist, the movement of the arm can be captured by estimating only the rotation of the elbow with respect to the shoulder and the rotation of the wrist with respect to elbow. So similarly, we can generate the positions of all the body joints by recursively rotating the human skeleton from the root joint to all the lip joints. And this process is called forward kinematics. Next, I'd like to introduce our proposed white pose deep learning model. We first transform the CSI data into a sequence of the input data. Then we employ a stack of the convolutional neural network to extract the spatial features from the CSI data. And we further use recurrent neural network, specifically LSTM, to capture the temporal dependencies between consecutive data samples. The key component of our framework is the forward kinematics layer, which can estimate the rotation of the joint from the extracted spatial temporal features and apply the estimated rotation to an initial skeleton to generate realistic postures. And on top of our model, we define 3 loss functions in order to the error in the estimation of the joint position and the rotation, but also can smooth the consecutive postures as much as possible. So let's look at the evaluation. So in this experiment, we employ a Wi-Fi testbed with 1 transmitter and non-receiving antennas around the human subject. As I mentioned before, we also use a Wacom system to generate the ground truth human skeletons. As you can see in the figure, the Wacom system is composed of 21 infrared cameras, and with 17 infrared markers attached on the joints of the human subject, the Wacom system can achieve less than 2 mm tracking error. In the experiment, we compare our proposed model with RF-Pose 3D, the state-of-art deep learning model for 3D human skeleton reconstruction. However, RF-Pose 3D is designed for only FMCW signals, not Wi-Fi. So we first evaluate our model in an empty room as shown in the previous picture. The performance metric we use here is the average joint localization error, which is the average Euclidean distance between the predicted joint locations and the ground truth. This table shows the average errors of each joint as indexed in this figure. We also calculated the overall result by averaging the error of all the joints. As we can see, our proposed Y-pose model can achieve much better performance than the baseline. And here we also show some examples of the generated 3D skeletons. As you can see, the skeletons constructed by our model are almost the same as the ground truth, while the skeleton generated by the baseline are quite distorted. This is because our model encoded the prior knowledge of the human skeleton to ensure that the generated skeleton satisfies the skeletal structure of the human body. And in contrast, the baseline just independently localizes each joint. So the generated 3D skeleton may be distorted due to the localization error. And we also investigate the impact of occlusion on our model. And in this experiment, we place some wooden screens between the subject and the receiving antennas. And as you can see in this table, so in this case, our proposed Y-pose model can still achieve good performance. So in summary, the wireless human sensing technique can overcome the challenges faced by traditional camera-based human perception solutions, such as the lighting, occlusion, closing, as well as privacy issues. So potentially, it can enable a new generation of applications by supporting more sophisticated interactions between humans and their physical surroundings. And this is the end of my talk. Thank you very much for the attention, and I'd like to take questions.
I think we have about 1 minute left, and there are no questions, Dr. Su, in the Q&A. So I think we're actually all set. I just want to remind everybody that we have a break, 15-minute break coming after this. And finally, just wanted to thank the 3 sets of speakers, Dr. Su, Dr. Yang, and my colleague Dan and his colleagues, Emmanuel and Akil. Thanks, everybody. Terrific talks.